Okay. So, we will continue with our discussion on radiative heat transfer that we were carrying out during the last lecture. And if you remember, I have introduced the rate law of radiation, where I have shown for a black body radiation that the energy flux is represented in terms of absolute temperature raised to the power 4. We have also made some discussion regarding reflectivity, absorptivity and transmittivity, and for opaque materials I have shown you the relationship that the reflectivity plus the absorptivity is equal to unity. And for a black body, whatever is incident, that also we have said that entire spectrum of energy is absorbed. So, there is no reflection, and a black body emits radiation in proportion to theta s to the power 4, which is the absolute temperature to the power 4. And in that context, I have Kirchhoff's identity also I have introduced, and where I have shown that the absorptivity and emissivity have identical values. So, I left you at a point during the last lecture when I just started to talk about the view factors or the radiation view factors. And if you remember that for gray bodies, if we say non-black bodies, the energy emitted by a non-black body, the ratio of energy emitted by a non-black body to a black body, that also I have indicated that this is equal to. So, if we from the rate law, we will know that what is the value of E b, and as I said repeatedly that this E b is proportional to theta s to the power 4, multiply it with Stephens-Boltzmann's constant, okay, which has a value that also I have given, I think is 10 raised to the power minus 8, and this is watt per meter square Kelvin to the power 4. I have also been telling repeatedly, do not write degree Kelvin, okay? It is Kelvin to the power 4, degree Fahrenheit, degree centigrade, but not degree Kelvin. So, and since this is known from the radiation rate law that E b is equal to sigma theta s to the power 4, a body emits characteristic radiation raised to the power absolute temperature raised to the power 4. So, therefore, a knowledge of emissivity, surface emissivity will allow us to find out this parameter, which is the characteristics of a non-black. So, whatever is the energy emitted by a black body, multiply that by the emissivity of this surface. Emissivity of a black body is equal to 1, okay, that we know, and you multiply this E b with epsilon, and you got it for a real body, which may be a non-black body. So, that allows us to estimate, and now we will see that, well, a body is emitting, if it is a non-black body in B I write. So, I will say that this is equal to theta s prime to the power 4. This is again a surface temperature, but now I have introduced. But the question now comes that we want to address in today's lecture and proceed further. First issue is that whether the radiation that a non-black body or a black body is going to emit, whether that radiation is going to be intercepted by another medium or another body or not. When you talk of, because we are interested not only that this is an object is not only emitting radiation, it may be receiving also radiation from an object. So, we are interested in engineering problems to find out that, for example, if there is an object and there is a furnace, then we would like to find out that how much is the net energy interaction between the two, and therefore, we will be concerned with calculation of radiation energy exchange. And if you have remembered, with this particular term, I have also subtracted theta, and as I said, I wrote this expression, and then this is theta ambient to the power 4. So, this is from the ambient whatever energy is receiving, and this is the theta s which is given out by the body, and this therefore becomes the net energy emitted minus energy received. So, this is a representation, or this is representative of the net energy which is emitted by the surface, okay. And this may be negligible at some point, but the radiation rate law, as I have already explained to you, that a body emits radiation which is characteristics of its absolute surface temperature. But as I said, all the radiation emitted by an object may not be received by the surrounding itself. For example, you can see that we have an object here, and suppose there is a enclosure here. Let us consider that both of them are black bodies. So, it has a temperature of theta 1. So, it will emit theta 1 to the power 4 radiation. Similarly, it has, it may be a black body, whatever radiation is incident on it. So, the energy which is emitted by this particular object is going to be 100% intercepted by the black body, okay, or the surroundings. So, but on the other hand, so the black body itself is completely enclosed, and the body can see the enclosure entire over 360-degree angle. But imagine that if we have a surface here and a surface here, okay, in that case whatever radiation is going to be emitted by this object may not be totally intercepted by this. So, this is going to be emitting radiation if it is the black body in accordance with theta s to the power 4 multiplied by sigma, but this radiation something will be flowing towards me, something will be flowing in this particular direction, and something is going to be intercepted. So, all the radiations. So, here in this particular formulation, the net energy which we estimate to be theta s to the power 4 minus theta I to the power 4, energy emitted minus energy received, a measure of energy received, and in this quantity may not be always true, particularly when you talk of radiation exchange and when you have this kind of a scenario as opposed to this kind of a scenario. Okay. So, we want to, as I have indicated in my last lecture before leaving, that we want to introduce a parameter called radiation view factor, which basically is denoted by Fij. And this radiation view factor, basically if you consider two bodies, then we will say that we will represent as F12. What does that mean? This essentially indicates that the fraction of the energy emitted by object 1 which that object 2 is receiving, that is the notation meaning. The radiation view factor, I repeat again, please note. So, this essentially implies F12 implies that the energy emitted by object 1 and which is received by object 2, and the reverse is F21, and there is no guarantee in this kind of a scenario that F12 and F21s are identical. Suppose if it is a point source, then there is a good possibility that all the radiations given out by this could be intercepted by this surface if the surface area here is proportion much larger than this surface area, but the vice versa is not going to be true. So, F21 will essentially represents that the energy which is emitted by object 2 and is intercepted by 1, we want to introduce that, and that will come handy when we try to calculate the radiation exchange between two bodies, whether black or gray, that we will see later on. And we know that energy, if we can calculate from the fundamental radiation rate laws multiplied by emissivity, then we can get the extent of radiation which is coming out from a body at a certain temperature. Now, let us consider two bodies, okay, which are exchanging, to introduce this concept and how one can calculate. So, I want to introduce now what is known in radiation literature as the reciprocity theorem. So, if you have two bodies, body 1 and body 2, we have theta 1, we have theta 2, and let us say that these are black bodies. So, therefore, I will say Eb1 is equal to sigma into theta 1 to the power 4. Theta 2 is Eb2, because I assume that they are black bodies, and as I will make that statement that they are, this analysis that I am presenting is not only valid for black bodies, but it is also valid for gray bodies and across the range of temperatures. Okay? And I will consider only, so I have not specified what is the value of theta 1, whether it is 100 degree, 200 degree, 400 degree, but the analysis presented here will be applicable to both gray bodies and black bodies as well as across the range of temperature of interest. Okay? So, here we will say that this is theta s, theta 2 to the power 4. So, up to this point, there is no ambiguity, and now we say that therefore, the radiation exchange between two bodies may not be the net amount of energy which is intercepted, which is given out by this, if this has a surface area of A1 and this has a surface area of A2, then I will say Q1 now. So, I will, it is a flux quantity. So, I want to calculate the net rate of transport. So, I will say that this is equal to sigma A1 into theta 1. This is at theta 1 to the power 4. This is the total amount of energy which is emitted by this object, which is maintained at a characteristic temperature of theta 1. So, similarly, we can say Q2 we can say is going to be equal to sigma A2 into theta to the power 4. Now, the two bodies are brought together. So, there is going to be, because theta 1 is theta 2 are different. So, there is going to be a net amount of energy which is going to be interchanged between the two. So, now, if I say that if I want to write out that what is Q1 net radiation exchange between 1 and 2. Okay. So, with respect to 1, I am now finding out that how much of radiation it is giving and how much of radiation it is receiving. So, that represents the net emittance here, and in this particular case we will say that look, this amount of which is coming out from this particular body, entire thing is not intercepted by this. Okay. So, therefore, the net we can say that this is equal to sigma A1 and then theta 1 to the power 4, the same thing, and I will write now F1 and 2. Because this could be all the energy given out by this object may not be intercepted, there may be another body here, there may be another body here. So, this may be giving out heat. So, all the heat which is given out by this particular object, okay, is not intercepted by this particular object. It is only when this quantity multiplied by F1 2, that is the energy which this exchange is relevant between the two objects, and this F1 2 we will know that this is going to be a value which is going to be smaller than unity. Okay. If you substitute a value of is equal to 1, then that will represent essentially this particular quantity, which is the total amount of energy given out watt in terms of wattage, okay, given out by the body 1, and this represents the which is relevance as far as the transport between this is concerned. The same logic applies here also, that this is going to be giving out some energy, it will go something is going to be interacting with object 3, object 4 and something here. So, I will introduce here that another parameter sigma A2 theta 2 to the power 4, and then I will say this is going to be F21. So, this is also what, and this parameter this can be negative or this can be positive, okay, depending on the fact that whether theta 1 to the power 4, the product of this quantity is greater than this or not. So, if this quantity comes out to be positive quantity, then I will say as far as the energy transfer between the two objects are concerned, this is receiving more heat from this object than it is giving to it. But that is not the complete picture, as I say again, because there could be object 3, object 4, object 5, object 6, similar analysis must come. I am just doing the energy analysis to show you the principle, when you talk about two different. Now, if we bring out the concept of suppose that the two objects are in thermal equilibrium, okay. So, to arrive at the reciprocity theorem, we assume that we are talking about thermal equilibrium, and thermal equilibrium essentially implies that we have theta 1 is equal to theta 2. So, in that case, if the two objects are in thermal equilibrium, so this is giving as much heat to this object as it is receiving from this itself. So, the net quantity Q12 is going to be equal to 0, and therefore, on the basis of this equation I can say that A1 F12 is equal to A2 F21, and this is what is known in the literature as the reciprocity theorem. This will be very handy when we will try to find out that whatever it is. So, now if we substitute that value And this, as I said, this will be valid, this correlation when you talk of energy exchange between two objects, this will be valid even for gray bodies. And I have considered thermal equilibrium, but it does not necessarily mean that it holds good at thermal equilibrium. It holds across the range of temperature of interest at all temperatures and at all wavelengths. Okay. So, therefore, this equation can be represented as sigma, because A1 F12 and A2 F21 is, so I can say that with respect to 1 2 I will write A1 F12 and we get theta s to the power 4 theta 1 to the power 4 minus theta 2 to the power 4. I will write again this expression because it is at the lower part of the board, you may not see. So, the net energy exchange, if you use this reciprocity theorem, then I will say sigma I can take out, A1 F12 I can take out, and then I can say this is equal to theta 1 to the power 4 minus theta 2 to the power 4. Substitute F12 is equal to 1, that means if the objects can see each other completely, radiation emitted by one object is intercepted completely by the other, in that case F12 is equal to 1, and then you get the original expression that you have written in the beginning of. Now, this is very important for us. The knowledge of radiation view factor is very important. I will give you a practical example here. Suppose we have, we cast ingots and slabs in metal industry, or castings for example. So, at any point during the heat treatment process or before we take the casting for further mechanical processing, what we do? We put the casting or a slab, loom, ingot, whatever you may consider, or a near net shaped product into a furnace, and inside that furnace we may have several, if you look at the cross section of the furnace, suppose this is the base of the furnace, and in furnaces basically typically we either introduce, there could be a vertical charging furnace or there could be a horizontal charging furnace into the. So, this is the solid wall at the base, and we have ingots which are sitting here, castings which are sitting here. Note that it is not that we can, there are furnaces where we have ingots which are being continuously fed. So, one ingot may be there sitting at the inside the furnace at 10 o'clock, the other may be sitting inside the furnace from 10:10, the other may be sitting in the furnace from 10:30, and so on and so forth, because we keep on continuously charging the furnace. So, therefore, the temperature of these objects are not identical to each other. It is, they are not in equilibrium, okay, in the worst scenario in the furnace. So, therefore, there is going to be a net energy exchange between the two. But imagine an ingot, if you look at from the top view, you will see there are so many ingots or so many castings which are in proximity, maybe hundreds or 50, number of castings are there, and all of them would be interacting, exchanging heat because they are at different temperature. I have not introduced them at the same, simultaneously inside the furnace. There is some amount of delta time lag between their introduction into the furnace. So, that the ingots are going to be in different thermal state in the furnace. So, therefore, we understand that their temperatures are going to be, surface temperatures are going to be equilibrium, they are not going to be in thermal equilibrium. So, not only from the furnace heat will come, but if this ingot is at lower temperature and this ingot is at higher temperature, there is going to be some amount of energy going into this particular ingot. So, and this to calculate from the furnace, while I can calculate it very easily because the ingot can see the furnace completely, okay, but I have to take into account that how much of energy exchange is taking place between the two adjacent ingots, and not only just two. It could be, if you take the top view of the furnace, the top view of the furnace will look maybe something like this, where we have one ingot here, another ingot here, another ingot here, another ingot here. That could be the cluster of arrangements, and you can, it's a typical geometrical pattern, and these geometrical patterns are also not, they are changing as a function of time. I can take out one ingot, the geometrical pattern is lost. I can introduce one more ingot, the geometrical pattern is lost. So, it is a dynamically evolving configuration inside the furnace itself, and therefore, we can see that there is not just F12 which I have introduced here, there could be F12, there could be F13, F14, 15, 16. So, in general, for calculation of heat exchange in industrial furnaces, what we need to do is view factor amongst a large number of ingots and for all different combinations, and this is a quite a complicated solid geometry exercise in order to find out the view factors. Now, I will show you that, for example, if you have, as I have indicated, that if this is 1, the furnace is 2, it is absolutely clear, there is no doubt about it, that the view factor is going to be F1 2. Now, if you have, for example, a square, it looks like rectangle, but suppose it is square, all sides are A, okay, and if you are talking of this surface vis-a-vis this surface, okay, and in a square, this is a square, this surface is 1 and this surface is 2, then the F12 is going to come out to be 0.6. If you change it to a rectangle, then this value is not going to be same. Okay? So, it is not quite obvious that this area is same as this area, but for a square how it becomes 0.6. So, a solid geometry calculation of insulation is to be carried out in this particular a case in order to find out. Similarly, you change of make the two sheets like this, one is like this and the other is like this, which are there is an angle in between the two. So, if you have and there, if the plates are of identical length, I think it is L sin theta, that is the so that is why it is called the geometrical view factors. In some literature you will find it is called radiation view factors, and somewhere it is also called geometrical view factors, but that essentially indicates that necessitates that you have to carry out elaborate solid geometry calculation in order to find out the radiation view factors of the geometric view factors. They are not quite obvious as it is shown in this particular. So, there are tables which are available for us. Okay, all of you may be knowing there are handbooks, logarithmic handbooks, there are slack chemistry handbooks, there are activity ternary activity diagram handbooks. So, we also have informations compiled on radiation view factors for different. If you go to the exhaustive literature on radiative heat transfer, you will be able to find out that for different configurations. If it is not available for such kind of a complex scenario, you have no option but to do the exercise yourself, so that you should be able to find out that what are the radiation factors. And there, in such context, what happens is you can apply the reciprocity theorem to reduce your task such that if you know Fij, you should be able to calculate Fji and so on and so forth. So, therefore, what we have learned so far, that a body emits its radiation, it is equivalent to its absolute temperature or proportional to its absolute temperature raised to the power 4. If the body is black, in that case the energy emitted becomes equal to the Stephens-Boltzmann constant multiplied by the absolute temperature raised to the power 4. Consider a grey body where there are going to be some amount of reflections. So, then you have to multiply that parameter, which is maximum for a black body, with an emissivity factor, which is emissivity is lower than 1, so that you get the corresponding energy emitted by a grey body maintained at that characteristic temperature also. And then we can modify it. So, a black body, using the concept of black body, I can get necessary information on radiation coming out of a grey body, and also I can find out that when there is an exchange, that what proportion of that energy is intercepted by different bodies which may be in the adjacent. Now, with this understanding, let us look at the energy exchange. Energy exchange between black bodies is given by this expression, which I have already told you, okay, and that also I have shown you that if you have because this analysis is done with black body. So, therefore, F1 when there you have F12 is equal to 1, that means they can see each other completely. In that case, this converts to this particular expression, but this analysis is done for black body. So, this expression is also valid for black body as well as grey body, as I have indicated already. Now, using this elementary knowledge, let us now see how can you calculate the energy exchange between two gray surfaces, and then I will add a third surface also, and then the concepts will be absolutely clear to you. Now, so we have two bodies, body 1 . So, this is, it is maintained at theta 1 temperature, and this is a non-black body, it is a non-black body. So, it is there is the adjacent body which is maintained at body 2 at theta 2, and there is a exchange of energy between the two. There may be theta 2, there may be theta 3, many bodies are there. So, this body, if you concentrate on this particular body which is a non-black body, we are not concerned about this, we want to, once we understand with respect to this, we will be able to understand about this also, but let us also say that this is a non-black body. Black body energy exchange is very easy, as I have indicated. Why non-black body energy calculations, exchange calculations are difficult? Because from this object we will have some energy which is coming incident on this surface, and because this is a non-black surface, some energy is going to be reflected from this particular surface. Okay? So, this body, so if you say that this represents the incident energy flux, that means it is watt per meter square, okay, that is the unit, and this G could be coming from not just body 2, maybe body 3, body 4, body 4, body 5, body 6. Let us now consider only second body. So, there is a second body which emits radiation, and this radiation incidents on this surface, and a part of this radiation is going to be reflected. But this body has a characteristic temperature, it has its own emittance, and that emittance is EB1 into epsilon 1. And what is that EB1? Theta 1 to the power 4. Had this body been a black body, there is no consideration of G, because whatever G comes in, that G is going to be absorbed by this particular body itself, nothing is going to be reflected. So, therefore, the energy flux, this is called the radiosity, the energy flux which is emitted by this particular object is actually composed of two components. One is its characteristic radiation, which is representative of its temperature, plus what part of G is being reflected. So, therefore, actual characteristic radiation, so EB1, had it been a black body, could have been this simply, okay. But in this particular case, what we have, what we see, that the energy flux is going to be J is the radiosity, and then we have to subtract from it rho into, and suppose this is we denote it by. So, J1 and rho, what is the rho? Rho is the reflectivity. So, G is incident and rho G is going to be, because this is the reflectivity of the surface material surface. So, this represents the contribution from the reflected component that we have to subtract, and this is the total radiosity, that means the total energy which is coming out from that surface, which is composed of two different terms, and this we are going to denote. This is actually the characteristics of them. Okay? So, and I will as per our, and this basically is this particular quantity corresponding to, this is a black body quantity. So, this is what we see, this is the characteristics of the body itself, because a black body emits the net amount of radiation which is given had this body been black body theta 1 to the power 4, but in this particular case the corresponding radiation is not this, but actually this is the representation of, or representative of the radiation which is characteristics of this particular temperature of this particular body. Now, let us look at. So, fundamentally we would say that we can represent J as rho g. It has two components, as I said. One is the characteristics of its temperature and the other is the reflection part. So, this is the reflective part, okay? And then I have said that if you have a non-black body, so assuming that this body is a black body EB1, if I multiply it with epsilon, that represents the characteristic. So, that is the two components, that is what we see here. Okay? So, let me write it down for you. So, the total radiosity for this particular case can be expressed in time is equal to rho g1 plus EB1 and epsilon 1. Convert this to a black body, rho becomes equal to 0, E becomes equal to 1, and then we find out that, well, the body is the black body. So, it is the total radiosity is equivalent to EB1, which is equivalent to this particular expression. So, there is no ambiguity as far as this energy conservation statement is written, and in this particular case then we can do, we know from Kirchhoff's identity that we have seen, because most of the materials we consider as opaque. So, we will say rho plus alpha is equal to 1.0, and if you remember, we consider this to be equal to 0, and we also know from Kirchhoff's identity that this is nothing but E. So, therefore, we can say that, look, we can represent this 1 minus epsilon 1, that is what it is. Okay. So, here from here we get alpha is equal to 1 minus rho or epsilon is equal to 1 minus rho. It is better to write, because this is the characteristics of the surface, reflectivity of the surface of 1. So, that should be denoted in principle, by I correct here, that is the right way of representing it. Okay. So, this is now the simplified expression, and from here, so I wrote it J1 is equal to rho 1 G1 plus EB1 into epsilon 1, and by removing rho 1 I write this particular expression, and from here what we can see that if we expand this is equal to G1 minus epsilon G1 plus epsilon 1 and EB1, and this now gives us G1 is equal to epsilon 1 into E1 EB1 minus G1, and that is what I was talking about, what I have written here, okay, that J1 minus, so this should be actually J1 minus G1, sorry, this should not be. So, what is the incident part? Incident part is subtracted from the radiation part, and that is what total radiosity, and that is what gives us the net rate of energy. So, we can say that from here we will be able to write down that it is Q1 is equal to epsilon G1. Now, we do not know what is G1, which is the material properties are known to us. We know the emissivity of the surface, we know the reflectivity, but we really do not know what is G1, that what is the incident part. So, we need to eliminate this G1, and here if you look at this, then this expression could be used to write down that J1 minus EB1 epsilon 1 divided by 1 minus epsilon 1, and that is what I should be able to write as G1. So, from here this equation can be established. Okay. So, what I do? I take this to this particular side. So, you get J 1 minus E b 1 epsilon 1, and then I divide it by this. So, that becomes, and so therefore, now I can substitute this E 1 okay, E b 1 minus G 1, and that is equal to J 1. So, this is now a simple high school mathematics 1 minus epsilon 1. So, if I have substituted it correctly, yes, I have eliminated J 1. Okay. So, this object is giving out the total radiosity, which is J 1, and this J 1 okay, had this object been black body, this would have given out an energy, that was the energy which would be emanating from it. But now, because this is a non black body, okay, so there is reflective component which is there in the total amount of energy emittance. So, it is not E b 1, but it is J 1, and this is the maximum possible energy. If the black body and a non black body, both of them are going in the same temperature, a non black body will emit lesser radiation, maximum radiation is possible from the black body itself. Okay. So, therefore, we can say that there is this represents the potential difference between a black body and a gray body. We will try to arrive at an equation or an expression of this. So, if you now look at this, so whatever is the parameter within the bracket, let me manipulate that parameter and arrive at a relationship where I say that this is equal to Q 1, this is still flux, okay, and this is E 1, and then if we manipulate it E b 1 into 1 minus epsilon 1, and then we have minus J 1, and then we have plus E b 1 into epsilon 1, and the whole thing is now going to be divided by 1 minus epsilon 1. And if we do it like this, then we have E 1 by 1 minus epsilon 1 is equal to, this is going to be cancelled, okay, E b 1 into epsilon 1 and E b 1 into epsilon. So, this is plus E b 1 epsilon 1, and from here I will get minus E b 1 epsilon 1. So, therefore, they will cancel out. So, what we get here is essentially a parameter which is E b 1 minus J 1. So, having said that E b 1 minus J 1 represents a potential difference between the gray body, black and a gray body. So, I can now write, if that is so, then therefore, this can be represented in this particular format, in which I can say that the denominator in this particular case will represent what is known as the resistance for this potential difference associated with the potential difference. So, a black body and a gray body, this analysis indicates that had it been, we have, this is the energy which is emitted. If we have a black body, I would have simply written it as this. There is no difference, but now that it is a gray body, so there is a drop in terms of the emittance potential, and that drop occurs because of a parameter which is associated. That resistance has no length scale. When we are talking about contact thermal resistances, or we are talking about thermal resistance of a cylinder, we were seeing that there we have the thermal conductivity as well as the thickness of the plate coming into the resistance term. But the resistance term for this potential difference happens to be exclusively related to the surface characteristics, okay, which is the surface emissivity itself. Now, if emissivity, you can see that this essentially what does this indicate? That if you take a black body and couple the black body with a added surface resistance to it, there is a surface parameter, then the body becomes a gray body. That is okay. So, if this is a black body and this is a gray body, so say between the two there exists a resistance, and that resistance is not because of the geometrical parameter, but that resistance is because of the characteristics of the surface or the surface emissivity value itself. So, therefore, I can say that look, if I am talking about two energy exchange between these two bodies, okay, they are gray bodies. So, I can consider 1 and 2 to be black bodies only, but add a surface resistance term to it, and that is going to be. So, I will convert, therefore, the non-black body, non-black body 1 is equal to black body 1 plus a surface, add a surface resistance, and you will get it. Non-black body 2, it becomes a black body 2 with surface resistance. So, I will say what is this? This is Q1, this is equal to EB1 minus J1 and 1 minus epsilon 1 by epsilon, and if I do not want to use the flux, I want to add the net rate of energy transport, then I will bring in the simply the area, and then I will say this is Q1, okay, and then I will bring in, because this entire param is quantity is to be multiplied by the area. So, I will bring that area here and I can represent it like this. Analogous to this, I can say Q2, the energy emitted by the second black body, non-black body, is EB2 minus J2 and 1 minus epsilon 2 into epsilon 2. That is what it is. So, I have now, because I know how to calculate the energy exchange between the black bodies. So, by adding a surface resistance term, I have converted the gray bodies into black bodies. Now, so I have black body, I have added that resistance is 1 minus epsilon 1 by epsilon. So, this is my EB1, and this has now become my J1, the gray body. Similarly, here I would say this is my EB2, I have added a resistance, and this is become now my J2, and this is 1 epsilon 2 divided by epsilon 1 A1. Okay, and now I am writing EB1, so I will not write this. Okay, E2. Now I want to find out the energy exchange between the two objects. Now, as I said, the same thing comes into the picture, that energy which is given out by this object is not emitted entirely by this object. So, this J1 will be giving, I will have the energy which will be given out by this is going to be J1 A1 into F12. If you are talking about, and this one here, so I will write it here. So, J1 A1 F12, energy which is emitted by the gray body, and or I would say energy which is emitted by the black body with a surface resistance, which is intercepted by the second body here. Okay, that is what it is, the total rate of energy, which is, so the net energy exchange I can say J1, J2, F2, A2 and F1. I can apply the reciprocity theorem, A1 F12 has come and A2 F21 has come. So, therefore, I should be able to calculate that whatever is the energy given out by this intercepted by this object, and this is the energy which is given out by this, but intercepted by object 1. So, the net energy exchange in this case are going to be is equal to basically J1 minus J2 into J1 if you use. So, therefore, we can cast this as Q. If you say, if you bring it in terms of area, because I have brought area into the account. So, the net energy exchange I will say Q 1 2 in this case is going to be is equal to J 1 J 2. So, these are not between the two black bodies, these I am considering between the two objects. So, there is a potential difference J 1 and J 2. If J 1 and J 2 are identical, so that means they are at thermal equilibrium, there is no energy exchange, and then if I bring in where 1 over A 1 and F 1 2, that is what also I can write. And here I can say that if I bring in area, right area here, then I will not consider EB 1, but that will be equal to my net rate of transport in terms of wattage, and same can be done in this particular case also. So, now, so this expression that I have written here, because I brought in A here. So, basically, and this essentially tells us that when we have two gray bodies exchanging energy between the two, in that case what happens is we have a surface resistance in this particular case. This also we could have shown there, and A1 F2. So, we want to cast it like this, because we want to talk it in terms of potential difference, and that potential difference, therefore, this becomes my resistance, and this resistance is the space resistance. So, therefore, there is now a resistance between the two objects, and that resistance is nothing but 1 by A1 F12. So, therefore, the energy exchange between two gray bodies, which I have shown here in this two figure, can be considered to be energy exchange between two black bodies at the same temperature, but there are three resistances to be considered. Two of them are associated with the surface characteristics or surface emissivities, which are called as the surface resistance values, and one is the space resistance values. So, therefore, I would say that the net energy exchange Q12 net should be EB1 minus EB2, and then we can say that this is going to be equal to 1 minus epsilon 1 into A1 epsilon 1 plus 1 by A1 F12 plus 1 by 1 minus epsilon 2 divided by A2 into epsilon 1 epsilon 2. So, either if I consider J1 and J2, then this becomes the energy expression, but as I said that I do not know J1, I know what is EB1, but I do not know what J1 is equal to in terms of its characteristic temperature, because there is a reflection component coming into the picture itself. So, I want to convert the black body gray bodies into the black body, and that is how by adding surface resistance I have converted it to black body, and then when you consider the black body energy exchange, then whether it is a black body or gray body, because the energy given out by one object is not entirely intercepted, we bring in the view factor, and that brings in what is known as the space resistance. So, therefore, we can also say that if you because you have taken Q12, these are essentially the same expressions actually, but that I do not know how to express J1 and J2, and I want to calculate these parameters. So, therefore, what I have done, I have removed this J1 and J2, and what I have done in addition to this, I have added in series because they are working in series, okay, and therefore, I have added to this two different components, two additional components, the surface resistance terms, and changed this J1 and J2 to respectively B1 and B2, and that is what becomes is equal to. So, these are essentially identical. So, the net word may be removed. Okay. So, we can also represent this equation in a relatively simpler form, because now what is EB1? I go to the radiation rate law, and that becomes is equal to theta s to the power theta 1 to the power 4. What is EB2? I go to the radiation rate law, and that becomes my theta s to theta 2 to the power 4. Okay. And if I do that, in that case what happens is, if I substitute this and then I bring in here, so we can say Q12 can be sigma into theta 1 to the power 4 minus theta 2 to the power 4, and then I can say that I will bring in here area A1, and therefore, I can write down that this is going to be 1 minus epsilon by epsilon 1, and then this is going to be 1 by F12, and this is going to be A1 by A2 into 1 minus epsilon 2, and this is A2. So, just manipulated A1 taken common out of this, 1 by A1 taken common out of this, and then if you take 1 by A1 common out of this, then that is the expression, and then A1 I take it to the other side. So, I get it here, and then I can represent this parameter as the net radiation, and then I can say this is expressed in this is not the radiation view factor, this is a effective radiation view factor, which comprises of the space resistance as well as the two surface resistance. So, we should, so given the temperature, so the entire task now, the surface area will be known, that once you can calculate the effective radiation factor, because these temperatures are known. Okay. So, we should be able to calculate that what is the energy exchange between the gray bodies. Okay. So, this is Q12. Now, we can add, for example, to this particular example whatever I have shown here, and suppose if you have one surface resistance, another surface resistance, and then we have surface resistance here, and then we have, okay. So, this is our, that is what we have learned, and this is the space resistance A1 F12, and this is 1 of minus epsilon 1 A1, and this is my 1 minus epsilon 2 into 1 E2 into A2, and then we can have, if we had a re-radiating surface, then you can say that there is a we can bring in the concept of a third body, and here you must understand that this is R is a re-radiating surfaces. So, again in this particular case what happens is that we have a space resistance between the two, and that because it is a re-radiating surface, I am not considering that there is a surface resistance attached to here. So, there is, and this is participating with this also, this is participating with this also. So, this we will have to calculate A1 F1R and A2 F2R. That values needs to be calculated in these two particular cases based on the geometrical consideration of the system. And in this particular case, these resistances are acting in parallel, for example, they are working in, this is working in series. So, you have to use the fundamentals from our high school resistance calculations, equivalent resistance calculations in series as well in parallel, in order to find out what is the effective resistance, and that effective space resistance needs to be substituted into this particular case itself. So, therefore, this if resistance now F12 is going to be a function of, also will depend on F1r and F2r. So, we have to consider this view factors in order to find out that what is. So, this parameter is essentially when you have three objects, if you have a radiating surfaces, what is essentially changed in this formulation is going to be this particular parameter, where F1r and F2r will come into the picture, and that is what I said, that F12 will now contain features of F1r and F2r itself. So, we can do multiple objects also, but as you increase the number of objects, obviously what we will see that the calculations will become much difficult. Two body problem, if I want to give you calculation, is a standard joint entrance examination issue, that if you have two body problem, you can calculate the net forces acting between the two bodies very easily, but increase the body to 3 bodies and 4 bodies, the effective force calculations becomes extremely difficult. So, we will continue. So, this gives us the reasonable coverage of radiative heat transfer, whereby we have introduced the radiation rate laws, and ultimately we have shown that all bodies are not black bodies. So, how to calculate really the energy exchange between two gray bodies, and this last formulation essentially indicates that it is by manipulating the resistances, surface resistance as well as the space resistance values, energy exchange can be between gray bodies can be very well dealt by knowing the corresponding theory from the black body energy exchange principles. So, we will stop at this. So, we have now studied heat conduction, heat convection, heat radiation, and now I am going to discuss in the next lecture that what are the application of whatever you have learnt in this particular course so far as heat transfers are concerned, because the heat transfer finds extensive application in metals and materials processing, because we are talking about high temperature operation. So, and we know that energy is money. Okay? So, to generate 1 unit of energy is to spend some money. So, therefore, what happens is energy saving is an important consideration, and that you can possibly do provided you know the fundamentals well. So, we will continue with the application of heat transfer theories to metals processing in the next lecture.